All right, section 8.4. This section covers the polar coordinate system and graphs of polar equations. Now, when I started section 8.3, remember I told you that over the course of the next few sections you would see a lot of the same calculations being done, just in different contexts. That's what's going to happen primarily in this section. A lot of the same things that we did back in section 8.3 with the complex numbers, you're going to see done dealing with these polar coordinates. The difference being the language, the context, the notation, that kind of thing. Right? So for that reason, like I said, always caution you about being careful not to get confused as far as what's being asked, or if things look familiar, it's like, well, wait, that's what we did in this other case. That's to be expected, because it's a lot of the same calculations that we do. They're just done in different contexts. Right? So for obvious reasons, that could be a little confusing, I think. But section 8.4 deals with the polar coordinates, polar coordinate system, right? Now, in a polar coordinate system, here's what we're doing. Not to confuse what we were doing with the complex numbers in that previous section, where we had complex numbers written in standard form, the a plus bi, and the trig form, the r cis theta, or that cosine plus I sine theta. Here what we're doing is we're representing a point in our normal rectangular coordinate plane, our xy plane. Because remember, with the complex numbers, we had to use that coordinate system where we had the real axis and the imaginary axis, right? So it was still a two-dimensional rectangular coordinate system, but what the axes represented was different. This is a completely different concept, right? So don't confuse the two. The polar coordinates, or the idea behind polar coordinates, is it gives us another way to represent the location of a point in our traditional xy plane, but instead of using those rectangular coordinates x and y, we use the polar coordinates r and theta. All right, now how we find r and theta is going to be exactly like we found r and theta in the previous section, all right, because it's all based upon the right triangle definition, or the XYR definition of our trig functions. Right? So it all keeps coming back to the same thing. So that's why I keep saying we're going to see a lot of the same calculations. It's just a different context and different language. All right, so we have rectangular coordinates of the form XY. We have these polar coordinates of the form R theta. But these are identifying the same point in our coordinate plane. We're just giving two different representations of it. We're changing up some of our terminology to describe the parts of our coordinate plane. The origin is referred to as the pole. It's still the same origin, it's still the intersection of the x and y axis. The positive x-axis is called the polar axis. Right? But again, it's the same positive x-axis that we normally use. We're just referring to it as the polar axis in terms of these polar coordinates, or the polar coordinate system. Our angle theta, which with respect to rectangular coordinates, we call that our angle in standard position. Remember, our initial side is on the positive x-axis, terminal side passes through the point. So that was our angle in standard position. Here we're calling it a directed angle. Again, it's the same angle, just different language. But it's a directed angle from the polar axis. Right? So in degrees, in radians, you'll see both used here as always. We could use both units of measure for our angle measure. The R value, right? We've called this a lot of different things, but basically it's still the distance of that point from the origin, or in this case, the distance of the point from the pole. We call it a directed distance, though, in this case. And there's a reason for that I'll explain as we go forward. There's a little bit more to the R here than what we've seen previously. Right? Every time we have talked about the R value, right, the distance of the point from the origin, we've always said that it was a positive value. Right? It's a distance, or it's the length of the hypotenuse of that right triangle, etc., but it was always a positive value. That's fixing to change in this polar coordinate system. So that's going to be one of the big differences between what we have done up to this point traditionally and how the context in which we're using it changes things up a little bit. But this is defined, r is a directed distance from the pole to our point. So plotting points in the polar plane. There's two components, right? There's two coordinates. You have r, you have theta. Now, here's what I was saying earlier. The r value can now take on either a positive or a negative value. That's why we call it a directed distance. So we have the coordinates r theta. When you are plotting a point in this polar coordinate system, start by finding or identifying your angle theta. In what quadrant, right, is that angle located? As always, watch the quadrant, watch the quadrant. And then depending upon the sign of the r value, if the r value is positive, then you go in the direction of that angle from the pole. If, however, your r value is negative, you go in the opposite direction of the angle from the pole, right? So there's a little bit different there. The r value can take on a different context now. And again, maybe look at it this way. Here's my coordinate plane, my coordinate system. If I have a point located out here, say the coordinates of this point are r theta. So that would be taking r to be a positive value. I move into the direction or along the terminal side of theta. Now also too with these, we're still just plotting points. Oftentimes we draw the lines just to, give a direction or show a distance. But these are still just points. You're not drawing an angle. You're not, anything like that. You're still just plotting points whose coordinates are r theta. In the other situation, if r was negative with the same angle theta, again, I would move or start with that angle theta, and then the negative r value would send you in the opposite direction. So this point, just say with respect to the other point, would have the same angle theta, but the negative r value sends us in the opposite direction. Right? That's the difference. So with that in mind, when you're plotting a point in the polar coordinate system, you always start with the angle, right? So locate your directed angle first. Right? My quadrant is angle theta. And then depending upon the sign of r, we either move in the direction of that angle or in the opposite direction, depending on positive versus negative r. Right? And the OP we're referring to there, that's that distance from the origin or from the pole, which I have labeled as O, to the point P. Right, so we're either moving along OP or we're moving in the opposite direction. Now here's something else that's a little bit different compared to our rectangular coordinate system. Right, when we plot a point in the XY plane using coordinates XY, there is only one set of ordered pairs that would represent a point in our XY plane, right? We have an X coordinate, we have a Y coordinate, and there's only one for each and every point in the plane. That's different in the polar coordinate system because I can use coterminal angles, right? So once we have our angle theta, our directed angle, we could also, as before, use any angle that's coterminal to it for angle theta. And now also because of this positive and negative r value, that opens up even more possibilities of different ways that you can represent points in the polar coordinate system. So in other words, these ordered pairs r theta are not unique. There's an infinite number of ordered pairs in polar form that can be used to represent these points in the polar plane. Oh, and something else I just remembered, in the last section, when we talked about the complex numbers, we had the standard form, the a plus bi, and we had the trig form, which was that r cis theta. And I also mentioned to you that that was also called the polar form or polar notation for the complex numbers. But I told you I wasn't going to use it because I didn't want to confuse us with this notation, right? So the polar coordinate system, calling this the polar form or the polar coordinates of a point. But notice it's very much the same as what we did to find the polar or trig form of the complex numbers. The only difference is R can take on a positive or negative value here. Right? So again, try not to confuse the two. That can happen, obviously. So let's say, for example, right? So let's plot a few points. Now notice the grid that we have here. So when we're graphing in the rectangular plane with X and Y, we have that rectangle, right? And if you want to, you draw a grid in, but it's all rectangular. Notice in the polar coordinate system, we have these concentric circles that are emanating out from the pole. That makes it a lot easier to identify the location of those points, because remember, we're starting with an angle first, and then once we determine where the terminal side of that angle is, we're either moving along that side or in the opposite direction, the distance of our units. So by drawing these concentric circles, that sets up the radius, right, your R values, and it makes it a lot easier instead of trying to do it in the rectangular plane that we graph using X and Y, right? So this is a typical polar coordinate system. That's what they look like. So let me just make this a little darker. If we wanted to plot, say, that point 345 degrees, point A. So again, always start with your angle. Find your angle first, and then move along the angle a distance of R units. And so I end up with my point at that location. So that would be the point whose coordinates are 345 degrees. So we'll go ahead and label that as A. The point whose coordinates are 2 pi. Right? So we start with pi, our angle, 180 degrees. So that'll bring me over to that left side. And then again, we move a distance of 2 units from the pole to our point. And that would be point B. Point C, we've got 2 pi over 3, right? And again, you're going to see radians, you're going to see degrees. So I start with the angle 2 pi over 3. That's our quadrant 2 angle. That would be equivalent to what? 120 degrees. Pi over 3 is 60. 2 pi over 3 is 120. And then we're moving a distance of 4 units from the pole. And there would be our point C. Point D. Here we're bringing in a negative angle. Nothing changes there. We still measure negative angles the same as we do previously. So negative 30 degrees would put me down at what, 330? And then a distance of 2 units from the pole. Right? So nothing changes there. We measure negative angles exactly the same way as we always have. Right. But here's the difference. We said for letter E, I've got negative 360 degrees. So when I'm going to plot that point, I start with the angle 60 degrees. 60 degrees is up here. But since my R value is negative, instead of moving in this direction to get to our point, we move in the opposite direction from the pole. All right, so a direct 180 degrees in the opposite direction. And again, we're at a distance of 3 units. So along that would put me at this location. Okay. So notice I could also represent that point using coordinates. If I wanted a positive R value, then I would use that angle, 240 degrees, with an R value of 3. So 240 would get me to the same location as negative 360. And so that's what we mean by the ordered pairs are not unique. Right? Every point can be represented using an infinite number of ordered pairs. And the last one, point F. So a negative angle, a negative R value. So I always start with the angle. So negative pi over 2, that's going to put me where? Down at 270. And then our negative 4 sends us in the opposite direction of 270. So I'm heading up towards 90, 4 units. And that would be the location of point F. Okay, so it is a little bit different. You have to watch your context. I keep using that term, but that's really what it's all about. A lot of the same things that we've always talked about, but context changes some of that a little bit. Right? So that's our polar coordinate system, and that's how we plot points within that system. All right, well, just like with our complex numbers, and we had the two different ways or two different forms. Let me get this to go down. Two different forms that we could express the complex numbers, standard form and trig form. Now we've got two different ways to represent points or locate points in our coordinate plane. So, being able to convert between the two. And it's pretty much going to follow the same process as before. All right, so I'm going to convert from rectangular coordinates to polar coordinates. All right, rectangular coordinates again, that's x, y. Polar coordinates, that's r theta. So I need r, I need theta. Well, to get r, we'll use Pythagorean's theorem, square root of x squared plus y squared, just as we did with the complex numbers. And to get theta, again, I have tangent, inverse tangent. You can use inverse sine, inverse cosine. Again, just as before, it doesn't matter which one you use. I'll do some with tangent just to practice a little bit with our tangent values. But as always, watch your quadrant. Right. Watch your quadrant, watch your quadrant. Now, you're going to know the quadrant of your point because you're given the rectangular coordinates, right? So you know which quadrant your point is located. So adjust your angle theta accordingly. Right? But then again, that's exactly what we did back in section A3. To convert from polar coordinates to rectangular coordinates. Right? So here I'm starting with our theta, and I need x and y. Well, we'll use the same process we use with our complex numbers. But instead of x and y, we had a and b there. Right? So x is r cosine theta, y is r sine theta. And again, that's the easier of the conversions, because all you're doing is plugging in r, you're plugging in theta, and then you're getting your values. Whereas doing the conversion from rectangular to polar, that requires a little bit more work. Right? But again, it's the same basic process. So I have a few examples. I will do a couple of examples where we convert from rectangular to polar, and then a couple of examples where we convert from polar to rectangular. All right, so number one, taking our point 4, 4. Now again, quadrant 1, because I want to make sure when I find theta, I have the proper angle based upon the quadrant in which our point is located. So we said again how we find r, pretty straightforward as before, using Pythagorean's theorem. R is the square root of x squared plus y squared. So 4 squared plus 4 squared, 16 plus 16, square root of 32, which would be 16 times 2, so that's 4 square roots of 2. And then I'm using tangent. Again, you could use sine, you could use cosine, whatever you prefer. But we know that the tangent of theta is y over x, right? That hasn't changed. So 4 over 4 in this case, or the tangent of theta is 1. And so I'm looking at theta equal to the inverse tangent of 1, again, with an angle that is in quadrant 1, right? So 45 degrees or pi over 4, right? Whichever unit we care to use. So then this point 4, 4 in rectangular coordinates can be represented with polar coordinates r theta, 4 square roots of 2, and that should be 45 degrees, not 15 degrees. Fix that. Okay. Now again, that's not the only representation. So I could find an angle coterminal to 45 degrees and use that angle as our angle theta. So if I add 360 to 45 degrees, remember coterminal angles, we add or subtract 360 from our angle to get a coterminal angle. If I add 360 to 45, I've got 405 degrees. So this point could also be represented using the same r with a coterminal angle of 405 degrees. I could also represent it using a negative r value. And remember we said again, if I'm going to use a negative r value, then I need to move in the opposite direction of my angle to get to my point. So in other words, if I start with this point located at 4 square roots of 2, 45 degrees. All right, so that's going to be, say, about up here somewhere. Then if I want to use a negative R value or represent this with a negative R value, I need to first start with the point that's over here so that the negative R value then sends you back this direction to the point that we're interested in. So to get the angle that we're going to use, we just add 180 degrees to this angle. So if I add 180 to 45, I get 225. That puts me down in quadrant 3. This would be, say, the terminal side of 225. And then the negative R value sends us back over here to quadrant 1 in the opposite direction. And I end up at the point that we're interested in, which is this guy. Right? So that's how you can play with negative R. So if you're asked to represent your point using a negative R value, once you find your angle, add 180 degrees to that angle. That will give you this one. And then the negative R value sends you back to your original angle. And that's how you handle that. Number 2. I've got negative 3 square roots of 3. All right, so first, that's a quadrant 2 angle, quadrant 2 point, excuse me. So a quadrant 2 angle once we get to that point, because x is negative and y is positive. So find r, plug in x and y, so r is square root of x squared plus y squared. Negative 3 squared is 9. 3 square roots of 3 squared, that would be 9 times 3, or 27. So I get square root of 36, or 6. A little bit nicer R value in this case. Then we've got the tangent of theta. Missing some of my notation on some of these. We've got the tangent of theta, which is y over x. So 3 square roots of 3 over negative 3. And simplifying, somehow my square roots got wiped out. So that would leave me with just negative square root of 3. So then theta would be the inverse tangent of negative square root of 3. Now again, with respect to the appropriate quadrant, quadrant 2. And that's the same, that's the game we had to play with our, knowing the function value and looking for the angle. I'm looking for the angle theta in quadrant 2, whose tangent is negative square root of 3. And all that implies, right? You got to watch your quadrant, use your reference angle. That's the easiest way with this. The angle whose tangent is square root of 3 in quadrant 1 would be 60 degrees, or pi over 3. So use that reference angle in quadrant 2, 180 minus 60, or pi minus pi over 3. And I've got theta equal to 120 degrees, or 2 pi over 3. So there's r equal to 6. There's theta in degrees and radians. Let's do radians this time since we did degrees last time. So I've got negative 3 square root of 3, 3 square roots of 3. I know what happened with this. I had to make some changes and some of these numbers got eliminated. So we'll fix that as we go. So there's our original point, negative 3 square roots of 3, which can then be represented in polar coordinates with r theta, 6, 2 pi over 3. Or if we needed to come up with some equivalent points, then again, you could take your angle and add, in this case, 2 pi, right? If I want a coterminal angle, and 2 pi plus 2 pi over 3, that would be 6 pi over 3 plus 2 pi over 3, would get us to 8 pi over 3. So that's a coterminal angle to 2 pi over 3. There's another representation for our point. If I wanted to represent the point using a negative r value, then again, you start with this angle, the original angle that you found. And in this case, I'm going to add pi to that. Or you could also subtract it. Right? You can go in either direction. You just want to go 180 degrees or pi units, plus or minus, to bring you to the other side, opposite side of your angle. So adding pi to 2 pi over 3, that'd be 3 pi over 3 plus 2 pi over 3, that is 5 pi over 3. And then that, using the negative r value, would get us back to 2 pi over 3. Okay. Different representations for the same point. Now, the conversion in the opposite direction, we said that's always the easier, the more direct process, because if I have a point represented using polar coordinates r theta, in this case 7 pi over 6, it's just a matter of plugging that into x equals r cosine theta, y equals r sine theta. Nothing more to it than that. I mean, you can make a note of your quadrant just to make sure everything turns out the way it should sign-wise. But that is a point in quadrant 1. How do I know that? Because first, angle pi over 6 is in Q1. Secondly, the r value is positive. Now, if that was a negative 7, the fact that my angle is pi over 6 does not mean that that would be a quadrant 1 point. Because if the r was negative, that would send me in the opposite direction of pi over 6, which would put us in quadrant 3. I mentioned that while I'm thinking about it, right? So 7 pi over 6 would say be a point over here somewhere. If instead I had negative 7 pi over 6, I still got the same angle pi over 6, but negative 7 pi over 6 would send me this way. And I'd end up with a point over here. Okay? So be careful. The angle, it's not just the angle that tells you the quadrant. You also have to take that in conjunction with the sign of your r value. So that is quadrant 1. And then again, we said we'll just plug that into, get our x coordinate, x equals r cosine theta, y equals r sine theta. Cosine of pi over 6, square root of 3 over 2. Sine of pi over 6, 1/2. So I've got x equal to 7 square roots of 3 over 2. Y is 7/2. So our polar coordinates, 7 pi over 6, could be represented in rectangular form as 7 square roots of 3 over 2, 7/2. Now, there's only one of those, right? The ordered pairs x, y in our rectangular plane, our rectangular coordinate system, those are unique, right? So there's only one representation. Number 4, a little bit different situation, but maybe not. I mean, it just depends on if you recognize something here or not. I've got this point r theta, 0, negative 60 degrees. So notice with r equal to 0, when we find our rectangular coordinates, right, r cosine theta and r sine theta, well, the fact that r is 0 simply means that r cosine theta would be 0 and r sine theta would be 0. I don't even care about the angle in this case. Okay? And just think about this. If I have a point that's located, if the r is 0, that's the distance from the pole. Well, if your distance from the pole is 0, where are you? You're at the pole. And the angle would be irrelevant. All you're going to do is just stand on the pole and spin around. Right? So it doesn't change your location in terms of the coordinates in the rectangular system. You're going to still be at the origin. Right? So if you recognize that any point that has any polar coordinate that has a point with r equal to 0, that's a point at the pole. And that's never going to change. You're never going to move off the pole. So the rectangular coordinates would always be 0, 0 in that case. But again, if you don't recognize it, you can always still, just like we said, run it through the x equals r cosine theta, y equals r sine theta. Polar equations, polar curves. Now, we're going to play a little bit with this. This is, I'd say the main focus of this section is what we just got through doing. Plotting of the points in the polar coordinate system and how we can represent those in ordered pairs r theta. and then converting between the two forms, the rectangular coordinates and the polar coordinates. That's the main focus of this section. This little look at the equations, just to give you an idea of what this is all about. Those of you that are, if you're heading into calculus, into Calc 2, we do a whole bunch with polar coordinate system and polar equations. Right? So you'll see this again if you're heading into Calc 2. We'll get into this a lot more detail. But so this kind of, give you a little idea of what these are all about. Now, depending upon the equation, some equations actually end up being easier or simpler to write in the polar coordinate system. Some are simpler or easier in the rectangular coordinate system. If you look at number 1, 5x plus 3y equals 4. If I wanted to express that using a polar in the form of a polar equation, because that's a rectangular equation, x and y. Now, you may recognize that that is the equation of a line. If you don't remember that ax plus by equals c, we call that the general form of the linear equation. We don't work with it a lot, but that is a linear equation, recognize it or not. If I wanted to express this as a polar equation, or I mean the conversion is pretty straightforward, because we could do exactly what we did before. I can let x, or replace x with r cosine theta, and I can replace y with r sine theta. And that gets us to this equation. So I mean, there's really nothing tricky to go from rectangular equations to polar equations. We simply replace x and y. Again, I'm missing a theta in there. Now, the equation just became a little bit more complicated than the original, right? The rectangular equation, 5x plus 3y equals 4, is a simpler equation. And then here's the other thing. When you're writing an equation in polar form, and I'm going to show you how to do this on the calculator here in just a minute. When you're going to enter an equation that's in rectangular form, in xy form, on the calculator, you always have to have it in y equals form, right? You always have to solve it for y. So 5x plus 3y equals 4, I can't put that into my y equals editor. I would have to solve that for y in order to enter it in. With polar equations, these are typically put in, or, well, not typically, these have to be in r equals form in order to put them into the calculator. Right, now, again, there's different ways that you can write it, just like the linear equation that we started with, 5x plus 3y equals 4, perfectly good equation. The equation that we have written, 5r cosine theta plus 5r cosine theta plus 3r sine theta equals 4, perfectly good equation. But it is typical for polar equations to solve them for r. So I factored out the r on that left side, and then I just divided by the 5 cosine theta plus 3 sine theta. And that would be our polar equation, r equals. Okay. Number 2, x squared plus y squared equals 81. Well, with this one, again, I could have done what I did with the previous. I could have replaced x with r cosine theta, y with r sine theta, and get something that looks like number 1. But instead, I did a recognition here, recognizing that x squared plus y squared is equal to r squared, right? So I can replace directly x squared plus y squared with r squared, and now my equation is r squared equals 81. Now, first of all, you should recognize what that is, is the equation of, right? X squared plus y squared equals 81. You better recognize it. We've been working with it the entire semester. That is a circle centered at the origin with a radius of 9. Right? R squared is 81, so r is 9. By replacing x squared plus y squared with r squared, this gets me an equation in polar form, because now it's in terms of r. Now notice there's no theta there, but that's fine. I have r squared equals 81, or if I do the square root, I get r equals 9. Now I could have plus or minus 9 there, because we said in polar coordinates, r could be positive or negative. Right? So we tend to gravitate towards the positive, but technically that could be -9 as well. But what I'm looking at, regardless, would be all points in our polar coordinate system that are a distance of 9 units from the pole. And that is exactly our definition of a circle, right? With our distance from the origin of 9 units. And that's what we had in the original Cartesian or rectangular equation. That's the other term we call it. They call it a Cartesian equation. Our rectangular equation, x squared plus y squared equals 81. That's a circle centered at the origin with a radius of 9. This is what it looks like in polar form. So actually in this case, I mean, and either one of these equations, neither one is really too difficult or too bad, but r equals 9 is even simpler. Right? But that's the equation of a circle in polar form. Simply r equal to a value, because theta doesn't matter. Every point that's a distance of 9 units from the origin or from the pole would lie on our circle. Now, converting from polar to rectangular, that's a little bit more problematic. All right, because like I said, worst case scenario, if I'm going from rectangular to polar, I can always replace x with r cosine theta and y with r sine theta, if nothing else. Number two, I was able to do it a little bit nicer using or recognizing that relationship to bring in r squared. But if all else fails, I can always use r cosine theta, r sine theta. If I'm going from polar to rectangular, that's a bit more problematic because you need a representation. You have to bring x and y into this thing. And really the only relationship we have is that x is equal to r cosine theta, y is equal to r sine theta. X squared plus y squared equals r squared. So I need one of those combinations to get me to rectangular form. So we're not going to work with these near as much. You'll see maybe an example in your homework converting from polar to rectangular. It's a lot easier though to go from rectangular to polar. But in the couple of cases that we do have, number 3 is r equals 3. Well, from what we just talked about with number 2, now we can recognize that, well, that's the equation of a circle with a radius of 3. And if I want to convert that or put that into rectangular form, well, I can just kind of reverse the process we did with number 2. I'll square both sides to get r squared equals 9. And then I can replace r squared with x squared plus y squared. And there's the x and y that I need in my equation. So there's our rectangular equation, x squared plus y squared equals 9. Number 4, r cosine theta equals 4. Well, again, that's, one of our direct conversions. We know that r cosine theta is equal to x. So our equivalent Cartesian equation would be x equals 4. And you should recognize what that is the equation of. In Cartesian form, x equals 4, or rectangular form, x equals 4. That's the equation of what? A vertical line, right? So r cosine theta equals 4 would also give you a vertical line. Now, also, keep that in mind too. I mean, we're looking at the same graphs. Whether you write the equation in rectangular form or polar form, the graph is still the same. And just like we said, those other two are circles. The number 1, we said that was a linear equation, 5x plus 3y equals 4. So if you were to graph r equals 4 over 5 cosine theta plus 3 sine theta, you're going to get a line. Okay? So the graphs are the same. We're still graphing it in the same plane. We're just using different coordinates instead of x, y, r theta. Okay? Lastly, calculator. I'm not going to ask you anything on a tab. Well, I say that. I may change my mind. So let me not say that. Graphing on a calculator. Okay? Just like we graph our functions of the form y equals, I said earlier, you can graph polar equations of the form r equals. To graph a polar curve on the calculator, here's a step-by-step process. First, go to your mode, and you know where we change our mode from radians to degrees and vice versa? Underneath that, there are 4 choices. There's function, There's PAR, which is parametrics. We're going to look at those in section 10.7. Then there's POL, which is our polar, and then there's SEQ, which is for sequences and series. Function form y equals, polar form r equals, parametrics, like I said, we'll talk about those in section 10.7. And then sequences, again, that's a Calc 2 thing. If you're heading into calculus and you're going into Calc 2, toward the end of Calc 2, we talk about sequences and series and what that's all about. So that's where that comes in. So you can graph any of those 4 types of equations on your calculator, provided it's in the proper form. Now, because we are, so set your mode to polar. Also make sure that you are set to radians and not degrees, just like we always do when we're graphing any trig function. Reminder there as well, your mode must be set to radians. Okay? If you have it in degrees, you're not going to see a proper graph if you see anything at all. All right? So make sure you're in radians. So we solve the equation for r if it's not already solved for r, and just like we would enter in y equals for our functions, we would put it in as r equals. Now, once you change your mode to polar and you hit the y equals button, instead of y equals, you're going to see a list of r equals. All right, so just instead of bringing up y1 equals, y2 equals, etc., you're going to have r1 equals, r2 equals, etc. It'll automatically make the change. The other thing, when you go to enter in your equation, when you have function form, we have that button with the x and theta and t and all that, right? There's that button on the calculator that you use to enter your variable and your variable, where verb will come from, your x, t, theta, and n, right? That's all those things on that button. Well, when you're in y equals form, when you're in function form, and you hit that button, automatically it puts in x. Right? When you're in parametric form, and so we'll talk about that in 10.7, it automatically is going to put in a t. When you're in polar form, as we are here, and you hit that button, it's going to put in theta. And then when you do sequences, it puts in an n. All right. So once you set the mode, that's the reason for you see all those little symbols on there. It changes the symbol to be more relevant to the context. Right? So you're entering your equation, r equals. So if I'm looking down at number 1, I would have 1 minus cosine theta. Then to graph it, and this is just really a recommendation. I mean, we typically graph in that standard window that r equals. That zoom standard view, that number 6, when we're graphing our functions in the xy plane. Recommendation to get a better looking graph or a more accurate looking graph using zoom trig. It's number 7 in the zoom window. You could also maybe do zoom number 5. That's the square view. That gives you a pretty good picture as well of the graph. But I find that the best view typically comes by graphing in the zoom trig. Now, something else to make note of. When we change our mode to polar mode, the settings in the window setting, there's some new settings there. You're still going to have x min, x max, y min, y max, and all that. X scale, y scale. You're now going to have settings for theta. There's going to be a theta min, theta max, and theta step. Because we're talking about an angle, and we're drawing an equation, or graphing an equation, where the input is the measure of the angle, I can have some interval of angle values. Typically it's 0 to 2 pi, and actually the default setting would have theta min at 0 and theta max at 2 pi, or it's going to approximate it, 6.28. But you could set that, again, to anything you want, and what you're doing is you're plugging, those are going to be the input, the angle values that you're plugging into your equation. All right, so the default is 0 to 2 pi or 0 to 6.28. Now the theta step, that's how fast it's going to draw the graph. For whatever reason, the default is 0.13 something, something, something. If you increase the size of that value, it's going to draw the graph faster. If you decrease the size of the value, it's going to draw the graph slower. Because what you're doing is you're telling it what values of theta you want to plug in. So if I have theta step like at 0.1 then it's going to plug in values for theta that are incrementing by 0.1. So it's plugging in more and more values the smaller you make the theta step over whatever this interval is that you've defined for theta min and theta max. And so if it's plugging in more values, it's going to take longer to draw the graph. Not such a big deal when you're drawing these polar curves. When we talk about the parametrics later, that's going to be a little bit more of interest to us, because we're actually going to be interested in seeing the direction in which the graph is drawn. I mean, it's still interesting to see too when you're doing polars as well. But my recommendation for the theta step, like I said, by default is 0.13. If you need to draw the graph slower or wanted to draw it slower, I would go 0.1, maybe 0.05. But if you make that too small, it may draw the graph really, really, really slow and take a long time to draw the graph through whatever interval you defined. So the default typically works fine for polars. That's at 0.1, 0.05 if you want something a little bit slower. Now, after that, this is really just, look, you can explore these on the calculator. All right, you have the settings. I would just plug in each of these and see what kind of graph you get. See what it looks like. You're going to get a lot more interesting graphs than you do when you're graphing just our normal y=, functions. Right? And we'll see the same thing with parametric as well. But polars tend to be the most interesting. So graph the function, r equals 1 minus cosine theta. The graph that you get there we call a choroid. Graph r equals 4 sine 2 theta, r equals 2 cosine 3 theta. You're going to get similar graphs there. Those are 4-leaved and 3-leaved roses or flowers, if you want to call it that. So you're going to get some little flower-looking things there. Graph your tangent. I don't even have a description for what that is. You can graph that and look at it. And also number 5, right? Sine theta over cosine theta. And so really, just plug in some different functions, plug in some different arguments, things like that. See what happens. You're going to get some interesting graphs with these. You can amaze your friends at the next get-together whenever we're out of quarantine and say, hey, look what I can do with my calculator. Look at these pretty pictures. All right, so, plug in some different functions, try some different combinations, see what kind of interesting graphs you can come up with. But definitely a lot more interesting than our basic functions. All right. But again, that's not going to be our main interest in this section. I said the primary interest is all about the coordinate system itself, plotting of points, ordered pairs, and then the conversion between the two forms, rectangular xy, polar r theta. Okay? And that'll be it for this section, 8-4.